let's get started. Welcome after the winter break, Trustworthy machine learning lecture. Some announcements for today. Exercise 2, you've done very well. You submitted. So the grades will be ready by the end of the week. Ankit is working on that. So, and now we have exercise 3 online. You can find it. And after the lecture, there will be a tutorial on the introduction of the exercise. So Lennart is here, is responsible for the final part of the lecture, the uncertainty estimation. For the exam, now there's registration link open. The link is in Discord. It's not official, but we want to still get an idea of how many people are coming to each exam because we don't want to print exams too much. So in the worst case, if you don't register and come to the exam, then you may not have the exam sheet. So please indicate which exam you're coming to. And I guess you know the rules, right? You can take exam 1 or 2. You can choose between the two, of course. But if you take exam 1 and pass it, then there's no way to take exam 2. But if you fail exam 1, then you can actually take exam 2. And the failure for the first exam will be forgotten. So it sounds like a system where it's also always beneficial to take exam 1 and you just fail and take exam 2. Yeah, that is partially true. And some people actually do that. And there's no way to stop this. But also, that's something that we cannot control. But also, if you're thinking between the choices exam 1 and 2, obviously for exam 1 you don't have much time to prepare. So we try to make exam 1 easier and less depth, basically, and exam 2 harder, right? To make the exams fair and comparable for everyone. Okay, so please keep this in mind. Any questions so far? Yeah, maybe I'll talk more about the exams in the coming lectures afterwards. So let me begin the final part of the lecture, uncertainty estimation, after OD generalization and explainability parts. I like to see uncertainty estimation as an essential building block. Once you have a system which consists of many AI systems, like machine learning-based systems. So I would say when you just have a machine learning model itself, then maybe you don't need uncertainty estimation. But as soon as you try to plug this into some bigger pipeline, then you start requiring these uncertainty estimation. So for example, when you have human in the loop, so for example, you have first part of the system where machine learning system is making some prediction, and afterwards you decide whether to have a human in the loop to look at the results from the machine learning system. You might want to kind of differentiate the cases where the model is very confident that it's right and the model wants some kind of second thought from a human reviewer, right? For this purpose, you need some kind of measure from the model itself, what it thinks about its own prediction. And also, when there are other kind of automated modules after the current AI system, you also want to kind of differentiate the cases where the model is absolutely certain that it's correct and the cases where it's not, to communicate the degrees of effort the subsequent systems may have to put into this. So instead of just prediction results, you need something else like uncertainty, which we will define more precisely in the coming slides. So I'm going to give you a bunch of examples where we might need uncertainty estimation. So I used to work in a company where um, there's a search engine, right? Um, and there's something called image search. Uh, and what they do is they let users take pictures, right, of some person on the street, right, and ask the search engine what is the brand for this clothing, right? And if the picture taken is always good, then there's no problem. But very often the case, they take very poor quality picture. In those cases, you might want the system to tell the user that maybe you have to take the picture again because I can't make a decision based on the picture given. Yeah. So if there's some kind of well, uncertainty enables this kind of interaction, yeah, with the user. Another example is when you have multiple modules in a bigger pipeline, where you have the task of object detection. Um, object detection is the task of finding all instances of some class in an image. So, for example, if you're looking for a person instance, um, a very old system that used to work not as well as the current systems, but at the time state of the art was something called RCNN. And there, how it works is it first generates like 10,000 different bounding boxes in an image. These are called object proposals. These are basically regions where the model believes that there's some interesting object, not necessarily of person class. And then there's a second system, which is doing classification for every box here, um, telling whether that's a person or not. So in this two-part system, if the first part does not tell the second part, um, the degree of likelihood of containing an interesting object, then the second part has to kind of go through all these 10,000 cases. And that's very expensive. Per image, right? Per image, you have to do all this computation then, and that's way too expensive. So what they did was they let the first part of the system attach a scalar value for every box, how likely an object is, an interesting object there is. And based on that, they can threshold, let's say, only top 100 or top 1,000 cases. And then that reduces the load for the second system much further without reducing the performance of the detection. And also, like when there's a high stake application like medical images, you obviously want to um, delegate some of the hard cases to human doctors again, right? So when you have to make a decision based on some medical image, um, in the cases where the model is absolutely certain and if there's an assumption that we can trust the level of certainty given by the model, then we can probably skip those cases where the certainty is super high and only ask humans when the certainty is lower than a certain threshold. And there's something called open set recognition. It's a classification system, but at test time, you are expected to encounter some of the cases where the image does not contain an object of known class. So it's some object, right? But the class is not one of the K classes in the softmax output of the model. In those cases, you also want to tell, instead of making the prediction among those K classes always, you want to have the capability to tell, in this case, I don't know. I don't know. I don't think this is part of the known classes at all. So there's a possibility that this is a completely new case. Yeah. In those cases, you also want to have some measure of uncertainty. Also, in general machine learning, when you also consider annotation as part of the model development procedure, you might want to, given budget, you don't probably want to spend all the budget on annotating just random cases. you might want to spend your budget on the cases where the model will learn a lot. Yeah. Um, and there are theories saying, or hypotheses saying that when the model is uncertain on some samples, these are the samples where annotations will benefit the model a lot. Yeah, so you first run the model on some data set and figure out which unlabeled data are returning high uncertainty. Um, and then they invite annotators to annotate only those cases. And that's going to save the annotation cost and bring the greatest utility from the annotation. That's active learning. And so uncertainty is also used for the exploration, exploitation trade-off. you know, Exploration and exploitation is kind of a concept when you have a learning agent where the agent can also play with the environment to learn about the inner workings of the environment and have gain some knowledge. And based on the knowledge, eventually the agent is kind of exploiting the reward. Um, so for some example of that is when you do Bayesian optimization, for example. You have a lot of knobs to turn and you don't know which ones are giving you the greatest rewards. For example, like it could be an optimization problem. Um, and you know for a certain region in the search space, um, you know a little bit of inner workings there. And you can basically exploit your reward in that vicinity. But also, you don't want to kind of spend all your resources doing exploitation. You might want to reserve some of the resources for exploring the other regions in the search space. Um, and for telling which part of the input space is exploration and which part is exploitation regime, you might use uncertainty estimation, because uncertainty estimation can probably tell you which parts are the ones that the agent has not encountered before and should be explored further. Now, some people define 2025 as the year of agentic AI, right? So if you've watched some of the talks from some visionaries in AI field, a lot of people are talking about agentic AI. And I think, sorry, this is a very typical case where you have a bigger pipeline of things and you have machine learning modules as part of the bigger system. And they are doing communications. So to explain what agentic AI is, um, it's basically a system of LLMs, right? Where LLMs can communicate with each other, where they have their own individual roles. Um, and they also have access to different tools in the world. So instead of just solving a single task given by a single prompt, when a prompt is given, for example, there's some orchestration kind of LLM who's planning out uh, which other agents should be doing which part of the task, and eventually the this kind of central agent is also collecting back all the information and then kind of processing this into a nice answer back to the user again. So in this procedure, for example, so here is one example of credit analysis, financial analysis, loan underwriting, and risk analysis. This financial application scenario. And there, maybe one of the agents is not doing the right job, right? Maybe it's failing. And when one agent fails to do the right job, then maybe the error propagates to the other agents, right? Because in some cases, the task consists of this chain reaction of, or kind of a series of actions that it has to take in order to reach the final solution. So if something goes wrong, then you may want to have the capability to maybe let it retry or ask another agent to do the task when someone fails, right? And for determining this, you will surely need some um, kind of inspection, like introspection of the agent by itself, what it thinks about the quality of the output. And for that, we're going to need some way to measure uncertainty confidence level for the output from an LLM. So that's it for the set of examples that I think is quite relevant for uncertainty estimation. So by now, I hope it's convincing enough that it's a very important problem to look at in 2025. So in general, my intuition is that you need confidence estimation if um, you have multiple outputs from a AI system and you don't want all the outputs to be treated equally. Maybe some of the outputs should be treated with less confidence and so on, right? And so if everything is perfect, like if every output of the AI system is perfect, then I would say we don't need uncertainty estimation. But I wonder if that will ever be the case. And so I think we'll probably need it for a long time. So let's get started with the definitions and evaluation, unless there's any questions so far. Okay, so uncertainty estimation is quite difficult to, like, uncertainty itself is quite difficult to define. And a lot of people, there are a lot of philosophical discussion of what you mean by uncertainty, what you mean by probability in the first place, right? There are different thoughts from Bayesian people, philosophers, frequentist people. Yeah, I was at a Bayesian statistics lecture some time ago, and he brought up like 10 different definitions of probability. Yeah, so that plus machine learning, yeah, you have a cross product to all different definitions, and I guess uncertainty will have very diverse set of interpretation for everyone around the world. So um, I'll take a simplistic view here and try to focus on the kind of definitions that people in this community care a lot about. And also it turns out to be rather practically important. So these are epistemic uncertainty and aleatoric uncertainty. So two possible causes of I'm not sure. Epistemic means I'm not sure because I haven't seen it before. I don't know what to do with this sample. Yeah, that's one case. The other case is I know this sample, but you're telling me to do different things for this same sample when you're training me. So I don't know what to do. That's aleatoric uncertainty. Okay. So let's go through each of the definition briefly. The next lectures will be kind of focusing on each of these in more depth. So we'll have more in-depth discussion. But for now, let's get an idea of what these are. I don't know because I haven't experienced it. That's epistemic uncertainty. And that, I mean, if you know Bayesian machine learning or Bayesian statistics, that probably reminds you of some of the principles from Bayesian statistics, right? If there's no experience, right, you have prior, and then experiences are kind of translated into likelihoods, right, in the Bayesian perspective. And this prior belief plus or times likelihood becomes your posterior, right? Of course, there should be some normalization. But anyways, um, so in Bayesian machine learning, there's the central object of interest is the model parameter, like the knowledge that you get from the interaction with the word or observation from the word. If there's no observation at all, then you have some prior distribution over the parameter space, and then you have observations, and based on some of the assumptions on the likelihood formulation, you may also get the likelihood of the observations for each of the parameters in the parameter space. And by combining these two factors, you have posterior over over the parameter space. So let me give you a better visualization of how epistemic uncertainty looks like in a simple machine learning case. It's like a tutorial, machine learning tutorial, right? So you have two classes, blue and red. And you can fit models for this binary classification training data. And I'm identifying three different models here: theta 1, theta 2, and theta 3. These are all valid solutions, right? Because these are separating the two classes. So, theta in this case is the space, like also a two-dimensional space, right? Because it's defined by the normal vector of the decision boundary. So the space of valid solutions in the parameter space will also be some region, right, in two-dimensional space. So try to imagine how this is like. So yeah, so if you have, so this is just basics. There's no epistemic uncertainty discussion yet. But if you have more broader function class, then you may have, like these nonlinear decision boundaries and so on. Yeah. Anyways, let's just consider the simplistic decision boundary case, like linear decision boundary. For this region, right, the second quadrant and fourth quadrant, there's no data. So P of x there is very low. So there's no exploration there. And therefore, that's the reason why we have this variance in the possible solutions. And think of this set of possible solutions, theta 1, 2, and 3, as some kind of posterior, right? We have posterior, which has large variance in this case. You have multiple different possibilities because you have not covered all the important regions in the input space. So the under exploration of some of the input space here translates to more variance in the parameter space after doing after training. So it's very important in this case to explore more from this OD region. It's also OD, right? So once you have more samples there, then you can determine which one of these models make sense and which one do not. So active learning is very relevant in this case, right? Because active learning will tell you that in order to reduce the variance in the posterior, you will have to sample more from this region. So these are the kind of cases where epistemic uncertainty matters. Yeah, the self-driving car only trained on daylight does not generalize well to a night case. Then you might want to sample more from the night case, and the way you do it is by measuring epistemic uncertainty. And hopefully the epistemic uncertainty is higher in the night case where you don't have many training samples. Yeah, it's also relevant for open set recognition case. We'll discuss more about epistemic uncertainty in the next lecture. Let's move on to the aleatoric uncertainty part. Any questions so far? Okay. Aleatoric uncertainty means I don't know, because you are confusing me, right, during the training. You have told me that for the same sample, sometimes it's class A, sometimes it's class B. So maybe what I'm going to do is I'm going to say, for this sample, the probability of class A is 60%, and the probability for class B is 40%. In other words, for the predictive task of predicting y from x, you can think of classification task. The true distribution actually has variance. P of y given x is not a deterministic function. It's a probabilistic distribution. And then we say there's inherent aleatoric uncertainty. So here's one example. So this is CIFAR images, and CIFAR images are very low quality images, and so even humans predict different classes for the same image in some cases. But of course, so there are like 10 classes in this case. So like plane, automobile, and so on. So for this image, yeah, everyone will still say it's an airplane and this is a cat. Yeah. But there are really cases where it's really hard to tell. Yeah, to me, it actually looks like a cat. Yeah. But some others report sheep for some reason. Yeah. This is even more problematic, right? A lot of people say it's deer, but I can also kind of relate to people who say it's a cat or bird, right? So these are exactly cases where even humans disagree. And what they were trying to do is to capture this human disagreement in the labeling, in the supervision as well. Because what people otherwise typically do is they just ask one annotator to annotate the image, and then or they ask multiple annotators and then take the max vote, and then train the model with this unimodal, like one hot label. But they were suggesting that we should probably train actually with this multi-hot label given by the human annotators. So these are exactly the case where you have high aleatoric uncertainty. So many people think of aleatoric uncertainty as kind of data corruption case, yeah? Even for many in the community. But I wanted to kind of let you know that it's not always the case. What is more important is not about the quality of data, but about the multiplicity of the possible answers for the given input. So if you look at ImageNet images, ImageNet is supposed to be a single label prediction task. So given an image, there should be one class. But you know there are 1,000 classes. So it's very likely that given an image, there may be actually a lot of classes belonging to those 1,000 classes. So here's one image labeled desk. And during training, you're going to train with this one-hot vector for the desk. And so all the other 999 classes will be suppressed. But in fact, this image contains other ImageNet classes like screen, monitor, and coffee mug. Yeah, so what's actually going to happen during training is you're going to have an image that looks like this, maybe not exactly like this, but something like that. And every time you see the same kind, like this very similar image, you'll have different supervision. Sometimes the model is trained to predict desk, sometimes predict screen, mug, right? That's exactly the case where you have, for similar data, you have different supervision. And that's what, exactly when you have aleatoric uncertainty. So it doesn't always have to be kind of corrupted image. This is one famous example that's also confusing to humans. Some people say it's rabbit, some people say it's dog, optical illusion. And of course, if you have some corruption, if we know that there's a possibility that some part of the digit will be concealed, then we know that this may be 17 or may as well be 47, for example. Or in other words, for the same, this kind of image, sometimes the label is given as 17, sometimes the label is given as 47. So the model basically has to deal with this mixed supervision. Yeah. This is typically the case when you also have missing features, which is related to the corruption of the input. Yeah. So if you have multiple features, the data points are well separated in this case, but if you project these data points to one of the axes, then you now have mixture of these samples. And when you have kind of mixture like this in some region of the space, then that's called aleatoric uncertainty. For very similar samples, you will see different labels. Yeah, and there are many other domains where you have measurement noise, blurry, noisy, low contrast image, low resolution image. There may also be cropping happening or occlusion happening, depending on how you process the data or how you capture. So any sensor data in general suffer from aleatoric uncertainty. Oh, and this is also quite important. For conditional generation, I would say that's also a case where we have high aleatoric uncertainty because let's say it's an image generation given a caption. Um, conditional image generation given caption. You may, for the same caption, you may generate different visualization like these, and there's no single right solution. And for any of these solutions, it's correct. So this is another case where we have high aleatoric uncertainty. Some people differentiate aleatoric versus epistemic uncertainty based on the reducibility. So when someone asks you, what do you mean by epistemic uncertainty? Do you mean reducible uncertainty or irreducible uncertainty? Then the answer is it's reducible uncertainty. And here reducibility means can the uncertainty get lower and lower all the way down to zero as we add more data? So reducibility with respect to additional data. That's what reducibility means. Yeah, of course, if you add more data, then by definition, the epistemic uncertainty in that region will go down. But if the true y-given axis has variance, right, then however many samples you sample from this region, you'll still see variance in y-given x. So this y-given x doesn't have anything to do with the number of data points there. Yeah, in lecture 11, we're going to talk more about aleatoric uncertainty, basically. To address this, addition of data is not a solution. We have to basically embrace the existence of variance in the possible answers. So we have to think of a suitable model architecture which is capable of expressing different possibilities, different plausible outcomes for the same input. And then think of a way to train this model correctly. Yeah. So we'll take a look at more examples of this in the next lectures, couple of lectures. Here's a little quiz, right? So which one is epistemic uncertainty? Left or right? Yeah. Yeah. Right one, yeah. Which one is aleatoric uncertainty? The other one, right? Yes, you're right. Here, some people also do uncertainty estimation per pixel. So, you know what semantic segmentation is? It's pixel-wise classification. Pixel-wise, you're classifying each pixel into road or pedestrian, sky, stuff like that. Pixel-wise, you can also measure aleatoric versus epistemic uncertainty using some methodology. And to me, that kind of intuitively makes sense here because you have greater aleatoric uncertainty for pixels where you have boundaries between concepts. So between the road, the street, and the pavement, the pedestrian, along the boundary you have greater aleatoric uncertainty. I think this is explained by the fact that annotations are not perfect along these boundaries. So for the same kind of boundary, some people like to say, are more biased to say, yeah, it's pavement. Some people are more likely to say it's part of the road. And so this mixture of signals will increase the aleatoric uncertainty along the boundaries of things. Whereas for epistemic uncertainty, it's kind of pointing to the regions where it's hard to explain really, but my intuition is that these are kind of unusual kind of cases that the model rarely sees, right? Like super, I don't know, it's hard to tell because I think it only makes sense if you have seen a lot of training samples for this data set. Um, but I can also imagine that like the 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 lower part of a car is probably something that you do not see a lot during training. So yeah, the point is that it seems to make sense to me. Oh yeah, there's a bigger image here. Um, so the next lectures, I'll try to explain epistemic uncertainty in lecture 10 and aleatoric uncertainty, and in lecture 12, I like to talk about epistemic uncertainty and aleatoric uncertainty together and how these are related. Maybe I'll talk about this third topic more in lecture 11 to let you also solve related questions in the exercise before the exercise deadline. I'll make sure that this is no problem. Okay, so after this, I wish to get a little bit more technical. Hmm? So we have defined stuff like in more hand-wavy way, but now let's talk about more mathematical formulation and more computational formulation. So what is the data format for uncertainty? We know what it is, what it's supposed to do, but how do you define it in your memory? Um, yeah, also like for the purpose of evaluation, it's important to quantify stuff, right? So I would say the simplest form of uncertainty estimate will be a scalar, yeah, a probability. Probability is a scalar that's between 0 and 1. And whenever anything is between 0 and 1, it's very interpretable. Like people like to think in terms of, people like percentages, right? And percentage is exactly a quantity that's between 0 and 1. And so we follow this practice. And instead of just letting a model output the final prediction, we let it also predict some scalar. I'm going to show you like different examples of going beyond a single scalar. You may also choose to report an array of scalars or a vector. So for example, maybe let's say the main task is to identify who the person is, yeah, person identification. Um, but instead of having a single scalar for telling how I'm sure about the prediction, you may also attach different uncertainty values for different factors of variation or different attributes, like hair color, eye color, and mouth shape, for example, to explain the source of uncertainty for the prediction. And it becomes a little bit more interpretable. And yeah, of course, we were talking about aleatoric uncertainty and epistemic uncertainty. So another option is to split the C of x into two different scalars, each accounting for different vectors. Here's one example how people have done it before. It's called "What Uncertainties Do We Need in Bayesian in Deep Learning?" It's kind of a classical paper in uncertainty estimation literature in deep learning. But okay, anyways, they propose these ways to get these scalars, aleatoric uncertainty and epistemic uncertainty, and came up with a way to train these quantities together through some learning algorithm, like the loss function and yeah, loss function basically. We're gonna touch upon this later on, so I'm just gonna skip it. The focus is more on kind of the possibilities to express uncertainty in different ways. Some other more complicated data formats that people have looked into, or I have looked into, is something called probabilistic embeddings as well. So instead of just having a scalar, you can also output a whole distribution. And if you have a distributional family defined, like Gaussian, right? And then you can express a Gaussian distribution through um, the, the, the mean vector and the variance matrix, right? Covariance matrix. So yeah, instead of a scalar, you can let the model predict the mean of the distribution and the covariance matrix of the distribution. And then that's equivalent to letting the model predict a distribution. So that's another possibility that could be interesting in other in other applications. But for basic evaluation, for now, we are sticking to scalar confidence values. Proper scoring rules. It gets a little bit more technical now. So, but before that, I like to kind of introduce the notion of predictive uncertainty. I'm throwing you different definitions of uncertainty now, but predictive uncertainty is just specifying exactly what kind of uncertainty you're caring about here. And predictive uncertainty is basically telling us that we care about a measure of whether I'm getting this correct or not, whether my answer is correct or not. Yeah, that's the definition of predictive uncertainty. It's related to both epistemic uncertainty and aleatoric uncertainty. The aleatoric and epistemic uncertainties are essentially identifying the root cause of uncertainty. So these are kind of about what is the cause of uncertainty. Predictive uncertainty is telling you what's the meaning of the uncertainty value that I'm looking into here. And it's basically telling you that, yeah, the value here means how likely you are to get the answer wrong. So, or correct, depending on whether you take 1 minus of that. So in lecture 11 or also in 12, we are going to look into the relationship between predictive uncertainty, epistemic uncertainty, and aleatoric uncertainty. So for example, some people like to kind of define predictive uncertainty as the sum of epistemic and aleatoric uncertainty as well. So there are some there's subtle differences in nuances how people define things and how they set up the relations here. So it's really hard to kind of give you one clean definition here. But we'll see a lot more examples in the coming lectures. So here, actually for the C of x, which is now supposed to indicate the likelihood of getting the answer wrong, there's actually ground truth for that. Whether you actually got the answer right or wrong, right? In the test set or in any annotated data set, you have this ground truth of whether you're correct or wrong, which we indicate in this case by L. It's a binary variable. You're correct or wrong. Whereas Y is indicating the ground truth label itself. So these are different, right? So your final model prediction is for getting the Y correct, and your C of X now is for getting the L right, in a sense. So you have now a secondary task along with your primary task. And now for training the model to predict the right C of X, to predict the L correctly, there are some probabilistic theories on what kind of loss function we need to train this. And it came from, like, the study of this came outside of the machine learning context as well, for like thinking about how to incentivize people to report their true belief about some probabilistic event. So let's say you want to bet on the probability of rain tomorrow. How do you set up the incentivization structure for the human to kind of be truthful about their their true probability, okay, their true belief. So here's the kind of formal setup where we define this gain, basically. So we let the subjects bet on the probability of rain, Q. So that's the internal belief of what they think is the probability of rain. And we're going to give them some rewards depending on the actual outcome. So ideally, if they think, yeah, it's probably going to be raining, probably. So let's say Q is closer to 1, close to rain, then if actually the rain happens, let's say L is equal to 1, which means rain, then you want to give greater reward for the person. And in the other case, where it does not rain, and the person actually predicted rain more, then we penalize this person. So the question is, how should the S of Q and L look like in order to encourage this person to make to earn the greatest money when their Q is according to their belief. So that's a question. And you know, L is a binary variable, so you can write down the expected reward from this gain as expectation over L of the value S of Q and L, which is exactly S of Q when L is 0 and times the probability where L is 0, and S of Q and 1 where probability for L equals to 1 is multiplied. Our goal is to find a function such that the maximization of this expectation is attained if and only if Q is equal to the true probability of raining. Yeah. So if that is the case, then the human subjects will do their best to really get the P of L equals to 1 correctly. Yeah. So they'll try to match Q as close as possible to the actual probability of rain. And there's no gaming of the metric in a sense by reporting it slightly different, maybe making a more conservative bet of saying, yeah, it's 50-50. And that should not give them greater reward than actually truly reporting the true probability of this happening. So formally, we say the expectation of S, Q, and L should be smaller than the expectation of S, P, and L, where Q is replaced by the true probability. So I'm writing P for the probability of L equals to 1. This is smaller for every Q in the range 0 and 1. And this is equality if and only if Q is equal to P. If S has such a structure, then we say it's a proper scoring rule. Okay, we're gonna take a look at more examples of this. So if you don't, if it doesn't become super intuitive yet, it will probably get more intuitive in the coming slides. So one simple example that I can think of is this linear reward. So if the person says the probability of rain is Q, and if it actually rains, then I'm going to give them reward of Q. So if they say, yeah, the probability is 1, and if it actually rains, then we give them $1 US. In the other way around, we have 1 minus Q, so if they report Q equals to 0, then they're going to get 1. But if they get completely wrong, then they're going to get 0 rewards. Okay, so it's linear in this way and linear in this way. It looks like valid rewards. But it's not a proper scoring rule, actually, if you take a look. Um, I wish to explain this, but this is set as an exercise for now. The outcome of this is actually that the predictor can maximize the expected reward by always predicting q equals to 0.5. So by just making a conservative bet, they can always maximize the expected reward. And so this is not a proper scoring rule. It's part of the exercise. I'm going to show you what is a proper scoring rule, an example of a proper scoring rule. So if it's quadratic, then it becomes proper, okay? So the reward is minus 1 minus q squared for L equals to 1, and for L equals to 0, it's minus q squared. Or the other way to write this is minus L minus q squared. So if you think of this as minus L minus q squared, the optimization problem is to, so this is a reward, right? So if you take the minus out, then it's a penalty, right? So you're trying to minimize the L2 penalty between the true answer and your prediction Q. So the smaller the gap is, you're going to get less penalty and more reward. So if L is 1, right, then the Q has to be close to 1 in order to earn more money. And it's a proper scoring rule. And I'm going to show you a proof for showing that, okay, here. Again, I'm going to write P as the probability of L equals to 1. And I'm going to write down the expectation of this value with respect to L by expanding this to two cases, L equals to 0 and L equals to 1. And I'm plugging in this P equals to P of L equals to 1. And the definition here. So when L is 0, no, it's minus q squared, right? So you have minus q squared, and this is 1 minus p. And then you have minus 1 minus q squared here, and this is p, right? And if you arrange everything nicely here, then you're going to have minus q squared minus p plus 2pq. It's very, yeah, it looks like nothing. But if you, okay, now the question is, when is this maximized, right? And the maximization problem here can be solved easily by doing gradient, taking the gradient, right, and looking for the stationary point, the first order condition for optimality. And if you derive this with respect to q, then you're going to have minus 2q, and this goes away, and plus 2p. And if you set this to 0, then q has to be p, right, in order to be at a kind of stationary, like local optimum, right? And it's very important to also note that the function is strictly concave, the second order condition. And so the stationary point is actually the local maximum, yeah? So a lot of people in the exam kind of forget to mention that, yeah, this is concave, convex, and so on. So they sometimes lost their points. So Q equals to P is the unique solution to this maximization problem. And that's why this so-called Breyer score is a proper scoring rule. Here's another example, log probability, which is given by the log of Q for the true case and log of 1 minus Q for L equals to 0. And it's also part of the exercise this time to show that this is a proper scoring rule. Okay, so again, the proper scoring rule was introduced as a way to kind of incentivize humans to report, do their best to make the right prediction instead of making some conservative prediction. we can use the same principle to kind of incentivize a model to predict this correctly. So we were talking about predictive uncertainty, right? Where L is the whether you got the answer right for this sample. And for C of X, we can think of ways to kind of incentivize the model to predict the true correctness. So let's jump into one application, one case. So let's say we have a binary classification task where the model output is f of x, which is indicating the probability of class 1. Okay, so when f of x is 1, then it's indicating that the probability of class 1 is 1. So class 1 is predicted when f of x is greater than 0.5, and class 0 is predicted otherwise. So it's kind of taking argmax between f of x and 1 minus f of x. Okay. Here we can define, so instead of having some separate parametric path to predict c of x, we can derive c of x directly from f of x by saying C of x is exactly the max between f of x and 1 minus f of x. So when f of x is greater than 0.5, f of x itself will be the C of x. Yeah. So when you're closer to the prediction of 1, your certainty will be higher. In the other way around, when your prediction is f of x is smaller than 0.5, then your confidence will be higher as your f of x goes smaller, right? That makes sense because now you're becoming more and more confident towards the prediction of class 0. Okay, so your c of x will look like this curve here, where p is f of x basically. So with this definition of c of x, we're going to take a look at the log probability proper scoring rule for C of x for the prediction of L, which is the correctness. How does the loss function look like in this case? Yeah, that's the question. So what does L equals to 1 mean here, where the prediction is correct? We can split into two cases. In the first case, we have f of x is greater than 0.5. So the model is predicting class 1, and the true class is actually 1. And then we are correct, right? So L is equal to 1 in that case. Or the prediction should be 0, like f of x is smaller than 0.5, and the true class is also 0. Okay, so these are two cases. And for the other two cases where the prediction and the ground truth do not match, we're going to have L equals to 0. Okay, so let's keep that in mind. And we can write down the proper scoring rule for C and L like this. So we're going to take log of C when the prediction is correct, and we're going to take log of 1 minus C when the prediction is incorrect. So you're going to see where this ends up in like 2 slides. I find this quite magical. It's kind of telling us that what we've been doing is not wrong. So you'll see that in a few minutes. So this is the formulation of the proper scoring rule for C and L. Let's take a moment to turn this S of C and L in terms of f of x and y, which we are more familiar with, basically. So we have these 4 cases where the ground truth is either 0 or 1, and the prediction is either 0 or 1. Okay. Let's take a look at the case where the y is 0 and the prediction is 0. In that case, we have correct prediction. L is 1. And so S of C and L will exactly be log of C of x, yeah, according to this here. And C of x, in that case, is 1 minus f of x. Why is that? Because f of x is smaller than 0.5. So by this definition, we can plug in 1 minus f of x in that case. Okay, let's take a look at the other case here, where the true class is 0 and the prediction is 1. In that case, we have wrong prediction. L is 0. And so S of C and L will be log of 1 minus C of x. And in this case, C of x is exactly f of x, because f of x is greater than 0.5. Okay, likewise, for the right-hand side, we have positive ground truth cases, and the prediction is 0, for example. In that case, we have wrong prediction, and so we can plug in log of 1 minus C of x. And C of x in this case is 1 minus f of x. So we have log of f of x eventually. And finally, we have correct prediction for the both one prediction. And in this case, we have log of C of x for from here for the correct prediction. And C of x is f of x, because f of x is greater than 0.5. Okay, and now we see that the formulation of S of C and L eventually depends only on the fact that the ground truth is either 0 or 1. So if the ground truth is 0, then you can just write down log of 1 minus f of x. Yeah, it's the same formulation here and here. When the ground truth is positive, then we have log of f of x in both cases. So in other words, we can write down this S of C and L into log of f of x when y is 1, and log of 1 minus f of x when y is 0. And that was a kind of a magical moment for me. I haven't seen this formulation before in any literature in this community. Maybe some people report this. But you know, the right-hand side here is exactly a binary cross entropy for training the model for the prediction of y. Yeah. You have f of x, which is the softmax, or in this case sigmoid output of the model, and you put log on top of that, and for positive you have log of x, and for negative you have log of 1 minus f of x. So this kind of means that if you train for the usual objective of binary cross entropy for class prediction, you're actually secretly also training for the proper scoring rule for C of x, defined as the max probability between the two classes, where C of x is given by this here. So this kind of justifies the use of max probability as a measure of predictive uncertainty, and the use of the usual binary cross entropy for a classification task. It's also secretly also training the C of x defined as the max probability to be the correct prediction of its own correctness. Yeah. So now the question is, how does that translate to multi-class classification cases? So here the claim is that cross entropy, likewise, which is defined for multiple classes, it's also encouraging correct confidence for the predictive uncertainty. It's not exactly proper scoring rule, but cross entropy is an envelope over the proper scoring rule for the proper scoring rule of the max probability for multi-class classification. So I'm going to show you how this is the case. So in this case, f of x is in this case a vector of k dimensions, an array of probabilities for each class k. And C of x is defined as the max probability among those k classes. Also max probability is a measure that a lot of people use in practice for measuring the predictive uncertainty. So, for example, on ImageNet, a lot of people use this max probability for predicting whether you're correct or wrong. Anyways, and now you can define a log probabilities proper scoring likewise as log of c if L is equal to 1 and log of 1 minus c if L is 0 as before. And we can plug in c of x definition here. So if L is 1, then we have log of max k f k x. And in the other case, we have 1 minus max. So we have sum over all the other indices than the argmax k. Okay. And the cases we can also write in terms of y and f. So basically, L equals to 1 means y is exactly the argmax, and this is the otherwise case. We can actually simplify the formulation that we've seen in the previous slide into S of CNL, which is now equal to log of Fy of x, where y is the ground truth class, and for the correct case, and f of y of x plus some other positive term for the other case. Yeah. Why is that? Why is that? So, argmax. Y is the argmax, right? So y is the true class, and true class happens to be the max probability here, and this is the max probability. So another way to write this down is replace k by y, because y is exactly the case where you have the max probability here. So you can just write this down as f of large Y of x. And here we are summing over k minus 1 values, and we know that y is not the argmax, right? So y should be one of the summands here, one of the terms, one of the indices that are being summed here. And so we can write down Fy of x first of all, and then we can write the rest of the terms in the summation, yeah, which is this part. And what I'm going to do is I'm going to bound this, right, from below. This can be bounded from below by log of f large Y of x. Yeah, right, because this term here is positive. These are some of probabilities. And we have log, which is an increasing function. So we can just bound this from below by log of f y of x. I know log of y of f of y of x is exactly the cross entropy loss, right? When you put minus. So if you're training for the maximization of this, then you're also maximizing for the left-hand side, which is the proper scoring rule for the max probability, for the prediction of the correctness. So this is also assuring us that the way we are training the model with this cross entropy, it's also secretly incentivizing the max probability to be the correct report of the correctness of the prediction. Yeah, I explained the slide here already. Is that clear to everyone so far? Okay. Stop me if you have any question. Now let's talk about evaluation. We talked about methodology. Actually, there's no methodology because it's just telling you that just keep doing what you're doing, right? And you're good. Just take the argmax, the max probability, and that should give you fairly good estimate of your predictive uncertainty. But you also want to, the fact that the loss is correct does not always mean that you're going to do a good job. Yeah. If the loss is kind of guaranteeing you to be doing a good job, then there's no problem with generalization, for example, in machine learning. I mean, that's the core issue with generalization. The loss is, yeah, no problem, but you probably need some extra regularization to make sure that is generalizing to new cases. Maybe there should be some more smoothing and so on. The same is true here, right? The proper scoring rule is giving you a good loss function for training this, but this does not mean that in the new kind of cases that the model encounters, the predictive uncertainty will do the right job. So how do you take a look at this? So proper scoring is a good loss function, but also it can be used as a good evaluation metric. So it's the same, right? You can also take a look at cross entropy, which is not exactly the proper scoring rule. We've seen that it's kind of a lower bound on the proper scoring, but it's easier to compute. It's simpler to compute, and there's kind of minimal change you have to make in the code. So what you can do is to take the average cross entropy over the test samples, and that's going to give you some number, and that's going to tell you how far away you are from a good report of your uncertainties for the correctness. So yeah, some people say it's NLL, negative log likelihood, on the test set, and you're going to see numbers like these, and I think lower is better. So yeah, the aim is to get as low as possible in this table. I know one of the problems with this metric is that it's not calibrated. We're going to talk about calibration later on, but if you have numbers that are kind of not bounded between 0 and 1, it loses interpretability actually, and you kind of don't understand very well what is the lower bound and what is the upper bound, and how is the gap? Is the gap big or small? There's no sense of this absolute meaning of the numbers. So you can only compare in relative terms. Like for example, in different data sets, you have different numbers, and also across different methodologies, different columns, you have different numbers. So you kind of understand, yeah, maybe this method is better than the others, but not in terms of like how far away you are from actually solving the task. In language model training, BERT models or GPT models and so on, there's something called perplexity, and perplexity is also slight modification of negative log likelihood. You just put take the exponentiation of the log likelihood, and you get perplexity. So by measuring perplexity, you are also measuring the predictive uncertainty for the language modeling task, actually. So yeah, just a small remark that yeah. And I wish to talk a little bit about calibration now. Even outside the context of uncertainty estimation, calibration is a very important concept in interpretability. Let's say your exam score is minus 141.59, right? Do you understand what that means, right? Maybe you can compare the numbers with others, right? Maybe someone else got minus 111, and maybe that's slightly better than this number. But when someone says the exam score is 84%, then we have better understanding of where this person stands roughly, right? And also it's probably easier to compare across different institutes and so on. So that's what I mean by calibration in general. But also in uncertainty estimation context. Calibration also means something a little bit more specific. It also means deviation from the true predictive uncertainty. So they like to draw this plot where on the y-axis you have accuracy, and on the x-axis you have different confidence beans. What you're doing is you're splitting your test samples into different beans according to the reported confidence levels. So on the left side, you have the bean where the model reports very low confidence in general. On the right side, you have samples where the model predicts very high certainty value. And you measure different accuracy values for each bean. And the hope is that the accuracy for each bean corresponds to the overall level of confidence level reported in each bean. Okay, so if the accuracy level exactly matches the reported confidence levels, then it's good. If it's far away, like this on the right side, then it's bad. So you're measuring basically the gap between the ideal calibration and the true state of the accuracies in different beans. So people like to kind of take a look at this calibration evaluation because the results are more calibrated. So we'll take a look at the comparison. How do you evaluate calibration? So I'm just formalizing what I just said. So here's the input x, and y is the output of the model, and let the model not just predict the y, but also some p hat. P hat is c of x that we've seen in the previous slides. They say the perfect calibration is when the probability the probability of predicting the correct class is equal to p, where p is the bean where the prediction is p. Yeah. So the exact procedure is like this. So you have some trained neural network, and you run this through some test data. You group the predictions into m beans, where each bean will potentially contain different number of samples, because you're not beaning according to the number of samples, but according to the confidence level for each sample. So in the worst case, maybe some of the beans will have 0 samples, and you can't compute the accuracy for that bean. And then you take the accuracy for each bean. So let's say BM is one of the beans, and you take the accuracy here. You can also take the average of the confidence values. You can also take the middle of the bean as the representative confidence level for that bean. But also you can, to be more precise, you can also take the average of the predicted confidence levels for each bean. And you, for each of the beans, you take the difference between the accuracy and the confidence level, and you basically average them over different beans, a weighted average. So you want to give more weight for the beans where you have a greater number of samples. And that's called expected calibration error, ECE. So ECE is one of the most beloved metrics people use in uncertainty estimation. So yeah, ECE, so there's ECE and there's MCE as well, which is measuring the max difference between accuracy and confidence in different along different beans. So you're kind of taking the worst case bean where the gap is greatest. Actually, the only reason why I introduced ECE is because it's a very, very problematic metric. And I think we have an exercise in the exercise sheet where we kind of understand how it's possible to gain this metric. And there's a lot of criticism on this metric, and I know people still use this metric. And in general, it's not a problem. But in the worst case scenario, if the people behind it decide to do something evil, then they can always get very good results by using this metric. So I wanted you to be kind of aware of the danger here and take a, with a pinch of salt, right? Um, and the metric also depends on the binning. So like the standard practice is to bin um, like introduce 10 beans, right? Um, but by introducing more beans than 10, for example, you can have like widely different values of ECE as well. And the diagram here is also called reliability diagram. I just wanted to introduce the terminology here. Um, so what do I like better than ECE then? I like NLL or the proper scoring rule, for example. I like the metric for relative comparison. But also I like ranking-based metrics. Calibration is requiring you to have a precise equality between the C of x, the predictive uncertainty, and the true likelihood of getting this wrong. But do we really need that? That's the question. We can aim for a weaker condition where we have only ranking condition. So I don't care where the range of C of x leaves. It can be from -100 to +100. Then it's not well calibrated, of course not. But probably we don't care as long as the ranking is correct. Meaning that when C of x is greater than C of x prime, for example, then the true probability P of x is also greater than P of x prime. Or when it's a predictive uncertainty, when you rank all the test samples according to C of x, then on the range of stuff where you have higher confidence values, you have greater chance of having L equals to 1, correct predictions. And for the other side, we have greater chance of encountering wrong predictions. As long as that kind of ordering is correct, I'm good. Part of the reason is because when we have the right ranking, we can always find a monotonic function, which is kind of mapping these uncertainty values back to the range of 0 and 1. And we can even aim for like fit a transformation function, which is now calibrating all these scores in the right way. in the right way. So when you have the right ranking, your calibration is only one monotonic function away. So to me, that's usually sufficient. And also in practice, people like to just do the detection, meaning that they just want to find a threshold, like operating threshold, and determine in which case you have correct prediction, in which case you have wrong prediction. And for finding the threshold, you don't really need calibration. You anyways have to kind of go through some of the samples and have human in the loop to determine what is the right threshold. And for that procedure, you just need the right ranking, not the right calibration. So how do you do ranking evaluation? Okay, so we start with two ingredients. So we have confidence estimates for each sample. So C of xi. We just write C of ci for each of these. And we have binary variable for each I, telling you whether that's a correct prediction or not. In the ideal case, we want to have C of I when ordered correctly. We're going to have a lot of ones in Li for the first part when you're doing descending order, right? Descending sorts. And for the other part, we have a lot of zeros in Li. And how to exactly measure that is by introduce concepts of true positive, false positive, true negative, false negative. Are you all familiar with all these four terms? Okay, and the area under the curve evaluation. Are you familiar with that? Like precision recall, true positive range, false positive range. Mm-hmm. Okay, then I'll probably do a little bit of recap and just stop me when anything is not clear. Um, so we have a plot like this, right? So on the right, on the x-axis, we have CI values. On the y-axis, we have LI values. Um, at each threshold, T, we have four different sets which are parameterized by the T value. And ideally, we want to have um, L to be 0 when CI is lower and vice versa. And the true positive, false negative, true negative, these are defined by these four, how to say, four regions defined by the T and L value. Okay. And for each T, you can also measure something like precision and recall. Or precision is the rate of these among true predictions. So among these samples on the right side here, how many are the green points here? And recall is basically among the L equals to 1 case, how many true positives are retrieved. So when T is greater, you're always going to see a greater, when T is lower, you're always going to see greater recall. But just to get this false negative here, you might actually introduce a lot of true negatives. So that's typically what happens when you lower the threshold a lot. So by running this threshold from from the minimum value of CI to the maximum value of CI, you're going to have a curve of precision and recall. So on the right side, when T is super low, then you're going to have big recall, like 100% recall, but generally low precision. You know? And actually, when you're retrieving every sample by setting T to be super low, your precision will exactly be the ratio of positive samples in your data set. And as you increase T and all the way up to, let's say, the maximum value of CI, you're typically going to have, maybe you're going to have the max CI value to be correct. Okay, then in that case, you're going to have precision 100% because you're retrieving one sample and that's the correct prediction. But your recall will be super low, like close to 0, because you're only retrieving one sample. So between these two extremes, the question is the curve looking good or bad? Oh, I have visualization like this. Nice. So you have precision recall. So on the one hand, you have perfect precision and super low recall. And on the other hand, you have good recall but low precision. If the classifier is good enough, then you're going to have this kind of squarish precision recall curve. When it's not good, then you're going to have something like this. When you have a detector or a classifier which has no idea what it's doing, there you're going to see something like this. Yeah, you converge to this random chance very quickly and then stay there as you increase T. And since you have a curve, you sometimes want to turn this curve into a single number. And the typical way you do that is by computing the area under the curve by using some numerical integration. So it's called AUPR, area under precision recall curve. One of the drawbacks, maybe you understand all this, but this is that the random classifier's performance depends on p equals to, the probability of the ratio of positive class. So let's say your task is super simple, like your test samples are super easy, and your prediction accuracy is 99%. In that case, your kind of positive set where L equals to 1 means you're correct. The prior is already 99%. So even for random detector, your AUPR score will be 99%. And so you have to basically magnify into this small range of 99% and 100% to kind of see all the differences. And typically, this is also dominated a lot by noises. So that's one of the drawbacks of using precision recall. So people rely on another metric, which is defined by true positive rate and false positive rate, where true positive rate is still recall the same. The problem is in the precision part actually. So instead of precision, they try to kind of a symmetric metric for recall for the other side. So among the negative, like true negative samples, how many of them are actually predicted as negative, or in this case, predicted as positive, is 1 minus each other, so it's the same. And typically, in that case, your random classifier will have a diagonal curve. And so regardless of how much imbalance you have in the test set, your random chance classifier will always give you 50%. So in a sense, it's better calibrated than AUPR score. It's called a ROC, where ROC is standing for the receiver, I forgot the name. Receiver operating curve, right? Characteristic, yeah. Yeah, maybe this comes from some other domain that I'm not so familiar with. And yeah, I'm more used to saying OROC, right, for this. And we have clear interpretation of 1 is perfect detector and 0.5 is random detector. So yeah, a lot of people really use this rank evaluation for predictive uncertainty. As you can see, AUPR is sometimes super weird, like very close to 99% in many cases, and it's super hard to make comparison. AUC, which is OROC, seems to be a little bit better. Yeah. There are some other cases where we are running out of time actually, but this is quick. So we had C of X as a predictor for the correctness of the predictions, but we can also do the evaluation for the prediction of OD-ness. So instead of L interpreted as correct predictions, we can use L equals to 1 as OD cases and L equals to 0 as indistribution cases. And here then we are interpreting C of X as the prediction of epistemic uncertainty. And one way to evaluate epistemic uncertainty is by doing this detection evaluation, where the task is to detect OD samples, where the aim is that your epistemic uncertainty estimate should be higher for OD samples and vice versa. You can do the same for corruption detection, which is supposed to be more related to aleatoric uncertainty. And if you have the ground truth labels for corruption versus no corruption, then you can also do the detection of corruption based on your uncertainty estimate and claim that this is, yeah, aleatoric uncertainty evaluation. Yeah, that's what I just explained here. Summary evaluations, we have looked into predictive uncertainty and epistemic uncertainty and aleatoric uncertainty. For predictive uncertainty, we can look at proper scoring rules like log likelihood, Brier scores. We can also look at calibration, like expected calibrated calibration error. We can look at ranking metrics like OROC, AUPR. For epistemic uncertainty, we can look at OD detection, which is also measured by OROC, AUPR. We can also look at aleatoric uncertainty, where we have ground truth labels for corruption or multiplicity of the outputs. We can also use OROC and AUPR. Yeah, so any questions?